This is a video on the double angle formulae, which can be derived very easily from the addition formulae, which hopefully you've seen on the previous videos in the green box on the right there. If we want to get a double angle formula for sine 2a, all we need to do is replace the b in this equation at the top here with an a. So sine a plus a is going to be sine a cos a. Remember, we're just replacing all the b's over here with a's, plus cos a sine a. And sine a plus a is obviously sine 2a. So the left hand side of this is sine 2a, and we've got sine a cos a plus another sine a cos a. So this makes 2 sine a cos a, which is the double angle formula for sine 2a. We need to do the same for cos and tan now. So if we replace all the b's in here with a's, we're going to get cos a minus sine a sine a. So that means that cos 2a is going to equal cos squared a minus sine squared a, which is the double angle formula for cos 2a. Although it's also worth noting that you can use this to get a couple more useful formulae for cos 2a, because we can also use the fact that sine squared a plus cos squared a equals 1 to derive the other formulae. So if we just take this and replace the cos squared with a 1 minus sine squared, we'll get 1 minus sine squared a minus, we've still got this over here, minus sine squared a, which will give us 1 minus 2 sine squared a. What we could have done, an alternative to that, is we could have replaced sine squared a with 1 minus cos squared a. So we could have taken this equation here and changed it to cos squared a. So this is just staying as it is, but we could have made this 1 minus, let's just get rid of this. So we could have made this cos squared a and then 1 minus cos squared a, and then simplifying that, that would give us 2 cos squared a, because we've got a minus and a minus here, so that would give us 2 cos squared a minus 1. So we've actually got 3 double angle formulae for cos. We've got this one, if I highlight these, we've got this one here, we've got this one here, and we've got this one here. So for sine 2a, we've only got 1 double angle formula there, but for cos, we can use any of those 3 we like. Moving on to tan, again, replacing all the b's in here with a's, we will get tan a plus tan a all over 1 minus tan a, which means that tan 2a is going to equal 2 tan a over 1 minus tan squared a. So that is the double angle formula for tan 2a. Now, it's very important you can derive these. As I explained on previous videos, it's unlikely you will have to prove these addition formulae. Well, certainly not. It's unlikely you'll have to prove the top ones, although possible. But it is very, very likely that you do have to do what I've just done there, which is deriving the double angle formulae from the addition formulae. Okay, so make sure you're all happy to go through this that I've just done. Okay, it's very common in exams to have to do this as part A of a question. For example, show that cos 2a equals 1 minus 2 sine squared a. So to summarize then, these are the these are the double angle formulae. Double angle formulae. And you do need to learn these. Oh, dear me, struggling here. You do need to learn these. They're not in the formula book. So the addition formulae are in the formula book, but the double angle formulae are not. So you need to learn them, and you also need to be able to prove these. So you need to be able to prove from the addition formulae. Okay, so what's the point of those? Well, here's an example where we need to use the addition formulae in order to solve this equation here. So we've got 5 cos 2x plus 3 sine x equals 4. Now we can't really solve this until we have either all 2x's or all of just 1x. So we really want to make this, we really want to get rid of the cos 2x. So you might want to think to yourself, which of these formulae for cos 2x can we use to substitute in there in order to get rid of the cos 2x and then be able to solve this equation. Hopefully you've realized that the most useful one would be the one with sine in, since we already have a sine over here. If we substitute this into cos 2x, then we'll have all sines and we'll be able to solve the equation. So let's do that then. If we substitute 1 minus 2 sine squared, sorry, these are all x's, not a's, into here, and then do plus 3 sine x equals 4. Okay, we want to solve that now. So this is just like the questions you will have done in year 1 probably. So it should be fairly straightforward from here. That looks like a quadratic in sine x. So get it all to equal 0. And you can just use your calculator here. This is just like having a quadratic 10y squared minus 3y minus 1 equals 0. So it's no different from that. So you can just use your calculator to solve this quadratic, or factorize. But however you do it, you should find that sine x here, sine x equals a half, or sine x equals minus 1/5. So we now need to solve this in the range 0 to 2 pi. Given our answers in radians, or 3 exact in radians, or 3 significant figures in radians. So again, this is something you're used to doing now. If you do inverse sine on your calculator of a half, it's 30 degrees in degrees, but it's pi over 6 in radians. And I like to use the cast diagram method to find the other solutions. So where is sine positive? Well, sine is positive here and here. We've already got pi over 6, so pi over 6 we can put here. It's going to reflect, it has to be in that quadrant there where sine is positive. So we've got pi over 6 and pi over 6. Don't forget that this is 0, pi over 2, pi, 3 pi over 2, 0 or 2 pi. So if we're going here to here, we've already got that one. Here to here, that's pi minus pi over 6. So that's going to give us 5 pi over 6. And there won't be any more in our range 0 to 2 pi for this one. But there might be some more for this one. So if we do inverse sine of minus 1/5 now, I got minus 0.201 for that. So again, I would use a cast diagram, but whatever method you usually use should be fine. So doing the cast diagram for this time, we've got sine is negative. So where is sine negative? Well, sine is negative down here and down here. So the first angle we've got is minus 0.201. So let's put that down there. It needs to go over into this quadrant, the other quadrant where sine is negative. So that will also be 0.201. And now we just find all our solutions. This is 0, pi over 2, pi, 3 pi over 2, and 0 or 2 pi. So if you find all our solutions, we've got this one here, which is going to be pi plus 0.201. Remember the question said to give answers to 3 significant figures if they're not exact. So pi plus 0.201 will give us 3.34. And if we go all the way around to this one, that's the same as doing 2 pi minus 0.201. So that will give us 6.08 radians. This is not in our range because our final range needs to be between 0 and 2 pi. So I think we've got 4 solutions to this. And so we can leave them. These are exact. These are exact. And these are 3 significant figures.